The world stands on the brink of a technological revolution, a seismic shift that promises to redefine the very fabric of our digital existence. For decades, silicon has reigned supreme, its tiny transistors powering everything from smartphones to supercomputers. But the era of silicon's dominance is drawing to a close, giving way to a new generation of revolutionary technologies poised to reshape the future of computing. Imagine a world where computers operate at speeds unimaginable today, effortlessly tackling challenges that currently lie beyond our grasp. Picture devices consuming a fraction of the energy, their performance enhanced by materials with almost magical properties. This is the promise of the post-silicon era, a future where quantum computers harness the strangeness of the subatomic world, and novel materials like ironwood push the boundaries of energy efficiency. This is not science fiction, it is the future that awaits us, driven by relentless innovation and a desire to push the boundaries of the possible. The journey begins by understanding the evolution of computing, tracing the path from the first transistors to the cusp of a quantum revolution. The story of modern computing is inextricably intertwined with the invention of the transistor, a tiny semiconductor device that revolutionized electronics. Before the transistor, computers were bulky, unreliable behemoths, consuming vast amounts of power and space. The transistor changed everything, shrinking the size of electronic components and paving the way for the miniaturization of computers. In 1965, Gordon Moore, co-founder of Intel, made a prediction that would become known as Moore's Law. He observed that the number of transistors on a microchip doubles approximately every 2 years, leading to an exponential increase in computing power. This prediction held true for decades, driving unprecedented technological progress and shaping the digital landscape we know today. However, Moore's Law is approaching its physical limits. Transistors can only get so small before quantum effects begin to interfere, and the heat generated by billions of transistors packed onto a tiny chip becomes increasingly difficult to manage. This limitation has spurred the search for alternative materials and computing paradigms, ushering in a new era of innovation. One of the most promising avenues in the quest for revolutionary chips lies in the realm of quantum computing. Unlike classical computers, which store information as bits representing 0 or 1, quantum computers utilize qubits. Qubits leverage the principles of quantum mechanics, allowing them to exist in a superposition of states representing both 0 and 1 simultaneously. This unique property enables quantum computers to perform calculations exponentially faster than their classical counterparts for specific tasks. Among the various approaches to building qubits, Majorana fermions have emerged as a particularly intriguing candidate. These elusive particles, theorized to be their own antiparticles, possess unique properties that make them ideal for creating stable and fault-tolerant qubits. While still in its early stages, quantum computing, particularly with Majorana fermions, holds the potential to revolutionize fields like medicine, material science, and artificial intelligence. The ability to simulate complex molecules, design novel drugs, and develop advanced algorithms could transform industries and unlock solutions to some of humanity's most pressing challenges. Section 4. Ironwood and the material world of chips. The search for revolutionary chips extends beyond the realm of quantum computing, encompassing the development of novel materials with exceptional properties. Ironwood, a material inspired by the intricate structure of natural wood, exemplifies this quest for innovation. This material possesses a unique combination of strength, lightness, and thermal conductivity, making it an ideal candidate for use in electronic devices. Ironwood's exceptional thermal conductivity allows it to dissipate heat more effectively than traditional materials, addressing one of the key challenges facing modern chip design. Its lightweight nature and high strength-to-weight ratio open up possibilities for creating thinner, lighter, and more durable electronic devices. The development of ironwood and other advanced materials represents a paradigm shift in chip design, moving away from silicon's limitations towards materials tailored to meet the demands of next-generation computing. These materials promise to enhance energy efficiency, improve performance, and enable the creation of devices with unprecedented capabilities. Section 5. NVIDIA, powering the future of computing. As the world embraces the post-silicon era, industry leaders like NVIDIA are at the forefront of innovation, driving the development of revolutionary chips and shaping the future of computing. NVIDIA, renowned for its graphics processing units or GPUs, has expanded its expertise to encompass a wide range of computing applications, from artificial intelligence to autonomous vehicles. NVIDIA's recent advancements in chip technology, including its Ampere architecture and Grace CPU superchip, showcase the company's commitment to pushing the boundaries of performance and efficiency. These innovations are powering the next generation of data centers, enabling breakthroughs in scientific research and driving the development of immersive virtual worlds. NVIDIA's contributions extend beyond hardware, encompassing software platforms and ecosystems that empower developers and researchers to harness the full potential of its revolutionary chips. This holistic approach to innovation is driving the convergence of various technologies, creating a future where computing is more powerful, pervasive, and transformative than ever before.